Thanks for joining this talk and for joining the session. I'm gonna talk about in the next, like, say, 20 minutes or so on the topic of integrating model-based systems engineering and simulation. I think that this is a topic that has been touched upon in a few talks already, like in the Dassault talk in the previous session. And what I would like to point out here is that I'm not speaking kind of as an AVL representative, but I'm speaking as a representative of a OSEP project called Smart SE. Some of you might already know Smart SE. About the Smart SE project, I'm not going into any details, what the project is or who is participating. There are 25 participants, or more than that actually, from different industries, automotive, aerospace, tool vendors, consultants, you name it. And what I would like to focus on is that Smart SE, one of the main motivations of Smart SE is to foster and promote simulation-based engineering. And as one aspect of that, to initialize and develop and industrialize standards. Namely, for example, the SSP traceability or SSP layered standard traceability. So this is kind of the context which my presentation is about. Now, this is my first time at the Modellica conference, and from what I understand is it is a very much simulation-focused conference. So to make sure that we are all on the same page, I would like to give a kind of a prologue about what systems engineering is, or about how system architects would kind of characterize systems engineering. So basically, and this has already been brought up multiple times, the major challenge that we are focusing or that we are facing nowadays is product complexity. So you have, on the one hand side, you have increasing complexity because of technological reasons. You have more and more technologies that you need to cram into one product. And you also have a rising complexity due to an increasing system scope. So nowadays, it's not sufficient anymore to develop a car, but you need to consider a systems of system because, for example, of car to X communication. So you have to face significantly and substantially increasing complexity, which means that you have in your development team more stakeholders with different backgrounds, speaking different terminologies, and you have the challenge of you need to kind of orchestrate all of them, like a conductor of an orchestra. And this is exactly where model-based systems engineering comes in. So MBSE is describes or defines itself as a framework to deal with product complexity, meaning that it proposes a framework to enable you to handle a large volume of connected and interdependent information. And at the heart of model-based systems engineering is the system architecture model. And a few colleagues of mine from the Graz University of Technology, they have tried to characterize different models playing a role in model-based engineering in terms of 3 dimensions: system level or level in generally, the domain and the discipline. And what is quite clear is that system architecture models are always on the system level. They cover all domains, all disciplines, but do not cover all domains. So typically requirements are not part of the system level model because they are part of a requirements management tool. But the system architecture model itself focuses very much on the behavior and the structure of your system under development. So you can kind of understand the system architecture model, which we focus on in this talk, as a way to capture system level information about your product under development. And basically the idea here is to use the system architecture model as a single source of truth. Now, to make this hopefully a little bit more tangible, here's a slide that I've taken out of our AVL internal training material on model-based systems engineering. So what we, within AVL, so just as a context, kind of one half of AVL is an engineering service provider. So we help our customers develop, say, powertrains, batteries, and whatnot. And within these engineering services projects, we actively employ MBSE. And this is what we in these projects typically use MBSE and the system model for. So we use a system model to define the use or to specify the use cases of the system under development, the structural breakdown, the functions, the behavior, the state machine of the overall system, etc. And to give you also another, hopefully even more concrete example, this is again taken from our AVL intern slides. This is kind of our understanding of systems engineering and what we use it for. So the starting point is the top of the pyramid, obviously, with where you define your targets and requirements. And systems engineering takes in these targets and requirements and it tries to, as already mentioned, orchestrate the different development activities, hardware development, software development, verification, validation, etc. And again, just to emphasize it once more, at the heart of systems engineering is the system architecture model. And we within AVL, we mainly use the system architecture model to, first of all, define the functions of the system, for example, the driving functions or the charging energy management functions. We use the system architecture model for defining the electronic or the EE architecture. So broadly speaking, high voltage, low voltage architecture, and also the thermal architecture, like thermal management system and control logic. And we are using to a very limited extent, however, the system architecture model to define rough geometric or mechanical boundary conditions. So hopefully now you have a rough idea of what a system architecture model is and what it can be used for. I'm kind of emphasizing this because today and also yesterday I've heard the term system model being used. And personally, I have a not that strong simulation, but a stronger MBSE background. And within the MBSE context, you also talk about system models, but with a very different connotation. So there's one system model in the context of MBSE, which is only, and in air quotes, only qualitative and descriptive. So you describe your system behavior, your system architecture, in a descriptive, qualitative way. And this model only has very, very limited simulation capabilities. You could, for example, simulate a state machine and the reachability of states, but not more than that. And then there's another system model, which I guess was referred to in this conference, which is what MBSE or system architects would call a system simulation model, which is on the contrary and or differently to the system architecture model, it's quantitative and executable. And it's very much defined by its simulation purpose. So there are these two system models which need to kind of distinguish in order not to get confused. And hopefully it's obvious to you that these two kinds of system models, they are very much codependent because the system architects on the top, they need information from the system simulation model, whether their system architecture is fit for purpose. So one example being that the system architect needs the information, can I get by with a two-wheel drive or do I need a four-wheel drive to satisfy my acceleration requirements? And the system simulation model, on the other hand, needs obviously input from the system architecture model in terms of what are the components, what are the interfaces, the intended behaviors, etc. So two different kinds of system models, and they are very much interlinked and codependent, which leads me to the mission statement of what we are within the SmartSE project are trying to achieve. This is actually a sketch, a very old sketch from kind of the founding father of SysML, Sanford Friedenthal. And from the very get-go, part of the MBSE and SysML vision was to integrate SysML with analysis models, so simulation models. But it works, and the Dassault talk has showed it works, but it kind of works ad hoc or currently ad hoc or for very specific tool chains. It not works generally. And this is exactly the gap that we within SmartSE want to address. We want to bridge this gap and ensure a standards-based and seamless interoperability. Now, I guess for time reasons, I will skip this slide because you most likely have already come across the credible simulation process framework and you know it. So let's move ahead. This is kind of another view at the topic. Part of the credible simulation or credible simulation process framework, whatever you would like to call it, is the credible simulation process. And obviously, we want to support the credible simulation process with the SSP traceability package. And as pointed out, the simulation is very much in codependent with the system architecture and MBSE. So what we would like to do is we would like to establish this link between MBSE and simulation based on standards. So what are our results? Preliminary results at the moment. What we have done within the SmartSE project, and specifically in a collaboration between AVL, my company, and Bosch, the company from Hans Martin and Thomas Schwarzkopf, we have developed a demonstrator or a proof of concept showing that such a interconnection between MBSE and simulation based on standard is actually working. It's working. So at the heart of this demonstrator is a, honestly speaking, quite simple model transformation tool, which takes the information from the system architecture model and spits out as output an SSP package, or actually an SSP traceability package. So in kind of the first iteration of the proof of concept, we just used a very specific part of the system architecture model, namely the internal block diagram, which defines the components, the interfaces, and connections of your system, and transformed this based on rules into an SSD file, basically. And I mentioned here it's quite simple and based on rules, so there's no fancy AI stuff involved yet. It's based on basically on a mapping table that maps system information objects from SysML to information objects in the SSP standard. So this is the basic idea. And since we are using SSP traceability actually now, we can cram a lot more information that's already available in your system architecture model into this simulation package for a simulation engineer to consume. So there are, for example, requirements or test cases or even engineering orders could be in your system architecture model. And you obviously, these pieces of information, they are relevant for your simulation tasks. So you can, or we can also include this information into the SSP traceability package and provide it automatically to the simulation, credible simulation process. And these are just some screenshots from the AVL tool Model Connect, which show, you can hardly read it or you cannot read it at all, but never mind, which show how a simulation engineer can consume this information within his working tool, being the simulation tool. What I would also like to kind of highlight at this point is, I've mentioned it already that within SmartSE, we seek to establish this bridge between MBSE and simulation based on standards. So not based on one specific tool chain, for example, from one specific tool vendor, but it should work for any combination of tools that you have working in your organization. And one implication of this kind of requirement is that we are not model transformation tool in the middle is not directly interacting with the system. For example, the source system tool, because this is very much tool specific. We would have to talk with the tool API, and every tool API is different. So we have decided to use a representation of the system architecture model that is as tool independent as it gets now, which is a so-called XMI file. It's basically a special kind of XML file that is standardized by the OMG standardization body. So we are not interacting with the SysML tool specifically, but we are just parsing an XMI file and producing out of that an SSP package or SSP traceability package for that matter. Okay, let's skip the screenshots. Now you might ask yourself, okay, sounds nice. It works. It's not rocket science to make it work, but what's the value in it? We haven't applied it yet in productive projects. And what the best that we could do at the moment is to give this proof of concept to show it to system architects, show it to simulation experts, and ask them to assess it, whether they see any value in it or not. And this is exactly what we have done within AVL. We have shown this proof of concept to our system architects, to our system simulation experts, and asked them, do you see any value in it? Do you think that this could improve efficiency at all? And what they did is they broke down the typical effort that is involved in creating system simulation models and thought about which of these kind of ingredients or kind of steps that you need to take in order to set up a system simulation model, which of these steps could be optimized. And the kind of the conclusion was that for the projects that we are doing within AVL, the kind of average, and it's just a rough estimation, the kind of average time that it takes for setting up a system simulation model is 19 weeks. And with automatically generating an SSP package, taking over information from the system architecture model, we can most likely reduce this effort to 6 weeks, which is actually a substantial gain. So this is the current status that we have reached within the SmartSE project. And I would like now to briefly talk about the next steps that we are planning for the remainder of this year and for the next year. The first thing that we want to tackle is we want to create a systematic list of information objects. So of information objects that are relevant for both MBSE and simulation. Why do we want to do this? I'll skip the examples. And why do we want to do this? Actually, this is just the list of information objects is, firstly, it's handy because it brings all of these SmartSE project participants kind of on the same page. But it very much comes in handy for the next step that we are planning, which is to define a systematic mapping between SysML v2 and the SSP traceability standard. Because you might have heard of SysML v2, it's kind of the hot stuff within the MBSE community right now. It's kind of the big thing that's going to be industrialized within the next couple of years. And we think that it's important to have as it says here, to have a systematic, robust mapping between the upcoming standard SysML v2 and the upcoming standard SSP traceability to, again, achieve our initial SmartSE goal of enabling a standards-based and seamless interoperability between MBSE and simulation, which brings me now to my conclusion. So I hope what you can take away from this presentation is that firstly, MBSE is kind of provides you with a framework to handle product complexity, and system architecture model are at the heart of MBSE. And hopefully I could convey to you that the link between system architecture models and system simulation models makes sense, also from a business point of view. And what we do within the SmartSE project is we want to enable this coupling, this integration of MBSE and system simulation based on standards. And our kind of midterm goal, I guess you could say, is to support this coupling of MBSE and system simulation by recommending a mapping between SysML, specifically SysML v2, and SSP/SSP traceability. So I guess that's it. I hope you could take away for something, at least from this talk, for you, get some inspiration, and I guess I'm open to questions now. Thank you very much.